started.
Okay, yeah, it's always a great pleasure to introduce and welcome our old student and alumnus of Chennai Mathematical Institute, especially when we are on the verge of starting a specialized center at CMI. It's nice to showcase the successes of one of our old students. Ronak Soni is today's speaker. He graduated from CMI with a BSc in mathematics some 10 years back, I think 2012. And then his world line took him to the Tata Institute for Fundamental Research, where he did his PhD with Sandeep Trivedi. Then a postdoc at Stanford followed. And right now he's a postdoc at the Department of Applied Mathematics and Theoretical Physics in Cambridge University. His interests are broadly in gravity duality and in the connection between geometry and quantum entanglement. I believe today he's going to cross even those two boundaries. He's going to tell us how to do space-time through entanglement. Welcome, Ronak, and you can start your talk.
Hello, everyone. Thanks for the opportunity to speak, and I sincerely hope that this center becomes a center for path-breaking research over the next years. Yeah, 1 second, and 1 second. Yeah. So I'm going to speak about how entanglement builds spacetime. Okay. So and if anyone has questions, please don't hesitate to just interrupt me because I won't be able to see the chat. So, yeah. So good. Today I wanted to basically do two things in this talk. The first thing is explain what the title means. So what it means, okay, which is really a review of a lot of maybe even hundreds of papers by this time, because this is a slogan. Entanglement builds spacetime is a slogan that is driving research in the broad field of time theory for a lot of people. Okay. The second thing is I want to, if I have time, I will also present my work on this, one of my papers on this topic with Louis Anderson and Omkar Parikar. Louis is now a machine learning person at Google, and Omkar is now at TIFR. The archive number is this, unless I messed it up. Yeah. So this is broadly the plan of my talk. So first question is, so the first step in explaining what this title means is to explain the two words. The first word is entanglement. Entanglement is an essentially quantum version of correlation. Okay. What I mean by essentially quantum, I mean that in a very precise and quantitative sense, entanglement is a form of correlation that cannot be cannot be mimicked by classical matter. The classical matter, of course, is the matter we interact with on a daily basis, which we see every day. And quantum matter is really small particles which behave in very different ways, as I'm sure most of the audience has some idea about. And entanglement is a form of correlation, which is too much in some sense for classical physics. That's essentially quantum. The second word, of course, is space-time. Space-time is exactly what it sounds like. It is a concept of here and there, now and then, and the most important thing about space-time is that it's classical. Okay, the distance between me and you, it's fixed. There's nothing crazy happening there. It's a fixed number. Whereas if it was a quantum, it would not be a fixed number. It would fluctuate wildly. Okay, so space-time is classical, and the main assertion of this talk and a lot of literature is that entanglement builds space-time. So this is a very surprising thing when you think about it. And think that something that is essentially quantum is building the most classical thing there is, which is the concept of place and time, right? So now I will spend quite a bit of time explaining what on earth this means and why it is a sensible thing to say. Okay? Good. So first, I want to start with an analogy. So if I go into my kitchen right now, there is a type of vessel. It's like a round-bottomed vessel. In Gujarati, we call it a tapela, and there doesn't seem to be an English word for it. So whatever, I'll just call it a pan. Okay. And if you fill it with water, we usually store water, milk, and so on in these things. And now imagine slightly disturbing this pan, right? What happens? What happens is that the water goes, ripples, right? This is something I hope all of us have seen. In fact, kids often play with these things and make these very intricate patterns of ripples. Very beautiful, right? But if you shake it really hard, well, it's not just ripples anymore. The water jumps up and down, right? These two different sorts of things one can do. In physics, we call them regimes. So the regime where we're shaking it slowly is what I call the regime of low perturbations, or small perturbations. Okay. And the thing to notice about the regime of small perturbation, which is when you shake it slowly and there are ripples, is that all the water is moving. Okay. But really, the only important part is that the surface is rippling. Rest of it is not important, right? So the description of all the water's motion, which is some 3D description with particles moving up and down and left and right and so on, has been packaged into this very nice 2D description of waves on the surface, right? 3D water to 2D waves. And you can actually get a lot of mileage out of just thinking about waves on a surface, as long as you want to describe what happens when you touch the pan slowly. Okay, this is called an effective theory. Okay, what I'm saying right now is completely obvious, but and these ideas are very important in physics, and they will be very important for what I'm about to say as well. The important thing about this effective theory is coarse graining. The claim is not that all the motion of the water is just ripples on the surface. When you play with the pans, there's some stuff happening under the surface as well. But we don't need to care about it. That is the claim. It's not that there's nothing happening under the surface. It is that all that stuff is unimportant. So you can coarse grain it away to just leave the simpler description of waves. Okay. Yeah. So these are two concepts, and the another hallmark of the effective theory is that it breaks down. And it breaks down very obviously when you shake the pan really hard, right? Good. So that is one thing. So these are two concepts that I want to introduce. The concept of a regime, which I will also call a phase. A phase and a regime are not quite the same concept, but they're close enough for our purposes today, and the concept of an effective theory. Every phase of matter has an effective theory. When water is ice, it is in solid phase, and there is an effective theory of how ice moves. It moves as a block. Whereas when water is water, it moves as a liquid. It's a different effective theory. Okay. So good. Another concept I want to introduce is that of an order parameter. So one very nice way to check whether you're in the regime of small perturbations where there are waves, or a regime of large perturbations where all the water is moving, is to just pour a very thin film of kerosene on top of the water. Which is why I made this line blue, because it's kerosene. And then see, just look at the water and say, okay, is the kerosene near the top, or is it mixed in completely? If we are in the phase of a regime of small perturbations, okay, the kerosene will be near the top. Let's plot it. So this is the depth of water. This is the surface here. And this is the bottom. And this is the density of kerosene on the y-axis. Okay. Now, when the kerosene is near the top, which means we're in the regime of low perturbations, what happens is that if it, all the kerosene is near the top, of course, so the graph will look like this. Like almost all the kerosene is bunched up near the surface. Whereas if you mix it really hard, one would imagine that you get a completely different sort of graph, something like this, right? Because all the kerosene is evenly spread through the water. So the way to measure which phase you are in, or which regime you are in, is to just ask, okay, what is the density of kerosene near the top? Say in some, what is the density of kerosene in this region? Here, if there's a lot of this is known as an order parameter. Okay, when this parameter is big, we are in the ordered phase where all the kerosene is on top. If the parameter is small, we are in the disordered phase where all the kerosene is mixed. Okay, so these are very simple. These are very simple facts. I'm sure all of you I hope all of you understood that. Now I want to say some things about entanglement and spacetime by analogy. What I want to say is that entanglement is the order parameter for the existence of classical spacetime. What I mean here is that whatever fundamental theory of gravity that we have, it will have states where the spacetime doesn't look classical at all. The distance between you and me will fluctuate wildly in some extremely high energy states. But there is a regime of small perturbations where it doesn't fluctuate, and in some sense, entanglement is the order parameter for that regime. Another way to say it is, and I'm going to say some slightly different things, but I will not distinguish between these two things during this talk, is that space-time is the effective theory for entanglement. Okay. What this second statement means that there is something that is highly entangled, And the smooth classical spacetime that we see is in some sense an effective theory for this system. Okay. It is another word that people use is emergent. It's not fundamental, it's emergent. It emerges at low energies. Okay. Good. Now, there's two questions that should pop up for you. The first question is, what is entanglement? I just gave you a very generic statement above, but we should know more. The second question, well, I'm sure that a bunch of you know what entanglement is already. The second question is, entanglement of what? Because entanglement is a correlation. You need to define two things to be correlated. So what are these two things that you're talking about? I will slowly give partial answers to the second question, but I will start with the first question now. Okay. So now let me introduce you to what entanglement is. So that was the end of my introduction. So maybe I can stop for questions if there are any at this moment.
There is none in chat right now.
Okay. Let me read it.
No, there is nothing in chat, he said.
Yeah, there's nothing in chat. We'll continue, I think.
Oh, none in chat. Okay. Yeah. Okay. Thank you.
I wanted to ask. So, is the order parameter similar or the same as entropy, or are there different kinds of order parameters?
Good. So I'm not being very precise. I think that when I say entanglement as the order parameter, there are many measures of entanglement, and in fact, no one measure is truly an order parameter. But it's a very imprecise sense in which entanglement is an order parameter. But to the imprecise level at which I'm working, any measure is fine.
All right, thanks.
Yeah. Good. Now, let me just give you a lightning introduction / reminder of quantum mechanics. In quantum mechanics, which is the physics of extremely small systems like atoms and so on, atoms and electrons, a state is some vector in a Hilbert space. Okay. A Hilbert space is a vector space with an inner product in it. And this is some physicist notation for vectors. We call them kets. And we call the dual vectors bras. The point being that the inner products look like brackets. Maybe let me put it this way. Okay. This is a bra. Good. And what Hilbert space is this? Let me define the Hilbert space by its basis. So it's basically the basis is in one-to-one correspondence with classical states of our system. So let me use an example here. I'm sure many of you are familiar with Schrodinger's cat, which can be either alive or dead. So the Hilbert space for Schrodinger's cat is the span of one basis vector corresponding to the live cat and one basis vector corresponding to the dead cat. Okay. Good. And one of the funny point of quantum mechanics is that the Hilbert space contains states like which are in superposition of live and dead. Okay. This is Schrodinger's cat, of course, which is neither really alive nor really dead. It is in a superposition of those states. Good. And an important point is that for every observable, there is a self-adjoint operator. So, for example, I can say okay, the observable of whether the cat is alive. Okay, I can say we can use the operator 1, 0. Okay, where 1, 0 acting on live equals live, and at 1, 0, sorry, an operator is a matrix, so a matrix that inherits the dead state is the measurement of whether the cat is alive. So if the cat is alive, it gets 1. If the cat is alive, it gets 0. And more generally, the X, if you have some state psi, okay, which is in its cat, for example, it might be the Schrodinger's cat state where it is superposition of alive and dead. We can say that the what do you say, probability of alive is equal to the diagonal matrix element of this operator. Okay, so this is called an expectation value. And this is a diagonal matrix element. Okay. And one operator that we will use is called the Hamiltonian. The Hamiltonian is an operator H whose expectation value, this is the average energy, this is basically the energy of the state. We define the Hamiltonian as being the operator whose expectation value is energy. Okay. Good. Yeah, and yeah. Now, so now let's consider there being two cats. Okay. Yeah. In the case of two cats, the Hilbert space of two cats is in fact the tensor product of the Hilbert space of one cat. What this means is that if, for example, you have two live cats, we can write the state of the two live cats as live tensor live. Or sometimes I will also use live comma live, because writing a tensor plot every time is hard and it just takes effort. Okay. And similarly, you can also have live comma dead or dead comma live, depending on the state of the cats. Okay. And also dead comma dead. And these four states form a basis for the Hilbert space of two cats. Yeah. That is the tensor product. And there's two concepts that you need to know. One is the product state. A product state is any state that can be written as phi tensor phi on the Hilbert space of two cats. Okay, so the cat one is in state phi, the cat two is in state phi, and they're completely different. No, cat one doesn't care about cat two. Okay, and the product state, the word product state is, I hope, self-explanatory. And then there's entangled state. Okay, and an entangled state is any state that is not a product state. So, for example, let me just give an example here. LL plus DD. L for live, D for dead. I just shortened it. So it is a superposition of both cats being alive and both cats being dead. Okay. Contrast this with the following state. This state is a product state. Okay. And it's two Schrodinger states. There's two cats and two uncertainties. The first cat can be either live or dead, and independently the second cat can be either live or dead. But the entangled state is one where if the first cat is alive, the second cat is alive. If the first cat is dead, the second cat is dead. You know, they're entangled. This is the correlation that I spoke of. You know, it's a it's correlated with superpositions. That is entanglement. And so that is the basics of quantum mechanics that I wanted to remind you of or teach you of. So we will think about in what comes two types of entangled states. Well, three actually. Three entangled states. The first is what's called the Bell pair or EPR pair. EPR stands for Einstein, Podolsky, and Rosen, who were the first people to emphasize the weirdness of entanglement. It's also called a Bell pair because Bell is the person who explained that entanglement, explained exactly how entanglement is something that is essentially quantum using the following state. So we take, and the Bell pair is the state we just wrote down actually. Okay. Both live and dead have equal weights. Okay. More generally, you can take H1 equals H2 equals CK. Now, where earlier we had C2, and say which is basically the span of k different linearly independent vectors. The linear span of, and the Bell pair, generally speaking, is I equals 1 to k, sum over I comma I. Yeah, good. This is the first example. More generally, you can have different weights for different pairings. So more generally, you can have sum over I comma j equals 1 to k, some matrix mij I comma j. Okay. The Bell pair is the case where mij equals delta ij by root k. The delta ij is a symbol for it's 1 if I equals j, 0 if I is not equal to j. Yeah. So and the rank of Mij in some sense is one very simple measure of entanglement. If the rank of Mij is 1, then we have a product state. If the rank of Mij is not 1, then we have an entangled state. And when the rank becomes maximal, it is a set of states that includes the Bell pair. Okay. And finally, I want to introduce the thermopyne double state. Okay. Thermopyne double state uses the Hamiltonian. Remember that the Hamiltonian was the expectation value of the Hamiltonian was the energy. That is what the Hamiltonian was. And it is a self-adjoint operator because every observable is self-adjoint operator. So it has some eigenstates. Okay. So eigenstates of Hamiltonian are known as energy eigenstates. Okay. And they're special because H acting on some energy eigenstate E1. So we usually denote a vector by the eigenvalue of some operator. So here it's E1. So here's the Hamiltonian. Okay. And the thermopyne double state beta is some normalization. Let's forget about normalization. e power minus beta over 2e sum over e. Okay. Now this is one way to think about this is that it's a realistic version of a bell curve. Okay, because high energy states, as you might imagine, are harder to access, and this factor here suppresses high energy states. This number beta, or rather this inverse, is known as the temperature, and it's exactly a temperature as we know it, which is literally 30 degrees C or whatever. Yeah, cool. So now that is my lightning introduction to entanglement. So let me say a few words about space-time, and then I will quickly go on to its onto the connection, and I will stop to questions here.
I don't see any chat questions.
Great. So now gravity is the is the force due to the bending of space-time. One picture people use is to put a ball on a blanket, and the blanket bends when you put a ball on it. I actually downloaded a picture, but it was supposed to be somewhere accessible, but I seem to have lost it. So you're going to have to make do with this. I'm very sorry. Yeah. So so space-time bends, and basically when the optimal path on a curvy space is very different from the optimal path on a flat space, and that is why gravity affects motion. Okay. Now, one of the most important things about gravity, from the point of view of quantum mechanics, is that it was known as diffeomorphism invariance. Okay, which is the following fact. Usually, suppose you're doing an experiment. One of the first things you need to specify is where you're doing the experiment. Where is the lab? Right? So suppose I say I'm going to do the experiment at the corner of my room. Okay. And now, so someone who's very annoyed at me comes and puts a planet somewhere. And because space-time itself bends, the corner of the room moves away. Okay. Now I need to define my point, corner of the room, such that it moves to the corner when someone puts a planet. Right? And this is very hard. This is in general a fairly non-trivial problem, and it is at the root of a lot of confusions in gravity. And we just call it diffeomorphism invariance. People who know what diffeomorphism means might be confused about the relationship, and I won't explain what it is, but it's deeply related to that fact. There are two diffeomorphisms. Okay, so hard to define points. Okay, but gravity also helps us out. Where it takes a give, where it takes it also gives, because gravitational interaction, we all know, is controlled by Newton's constant, which in the real world is 6.6 into 10 power minus 11. This is where I show my skills of opening Wikipedia, because obviously I did not remember this. Okay. And okay, the number is not so important. What's important is the meter cubed per kg per second squared at the end of it. Because the Newton's constant is dimensional, it has units, which means that it makes sense only in relation to other things which have units. Okay. The number that actually controls the strength is actually Newton's constant over length cubed into mass into time squared. where LMT are length, mass, and time in the obvious way. Okay. This is the real. This is the strength of gravity. Okay. Right. The thing to notice is that the length is at the bottom. When you take really large length scale, the number goes down. So if you're in a regime where everything is very far away, gravity is very weak. Okay. And this kind of helps because when gravity is weak, this diffeomorphism invariance problem is also not so important because it's very hard to move points when gravity is weak. Okay. So we usually like to think about things in gravity in relation to places where things become very far away. Good. And this is actually very generic on a certain type of space, which is the following. Take a hyperbola and just rotate it to make a hyperboloid. Okay. As you go up, the distances between points become very far away on the hyperboloid because as the hyperboloid size goes up to infinity. This is a typical example of a negatively curved space. Which we also call anti-de Sitter space or ADS. Maybe I'll write anti-de Sitter. This is another place where I intended to show a picture, but I lost it. I'm sorry about that again. But it's a hyperboloid is a reasonably familiar object, I think. So yeah. Now let me draw the picture in a slightly different way. I'm going to draw a cylinder. Okay. Each slice of the cylinder, this slice here, is a hyperboloid. Okay. And this here is time. So space is a hyperboloid and this is time. So this is a three-dimensional radius space. Because the hyperboloid was 2D and I added time. So yeah. And again, so the point is that the boundary or the conformal boundary is just a cylinder without an interior, right? And basically, the conformal boundary is basically I'm isolating the parts where stuff becomes infinitely far away. So gravity becomes infinitely weak. So here there is gravity. Here there is no gravity. Okay. And it turns out that there's something very deep here, which was discovered by Maldacena in 1999. That there is a specific type of quantum mechanical system called a CFT, which is called a conformal field theory, but the statistics won't be important. It's a quantum mechanical system. Okay, yeah. That in some sense lives on this 2D space and has no gravity. And there is a relationship that ADS3 equals CFT2. So every experiment you can do in 3D ADS space with gravity is equivalent to an experiment in 2D, this 2D quantum mechanical system without gravity. Okay. And this has driven, thousands, tens of thousands of papers by now in the last 20 years. And it's extremely deep because one of the hardest, gravity is very hard in many ways. Quantum mechanics is not so hard. We know a lot about quantum mechanics. So we actually have learned a lot about gravity using this duality. These things are called dualities, where two seemingly different systems of the same system, they're called dualities. Cool. one of the elements of the duality is also correspondence between states. And it turns out that the thermophile double state that I defined in the CFT is dual to what is known as an eternal two-sided black hole. Okay. Now, HCFT.
Sorry, I have a question here. Okay.
Yeah.
So the thermophile is in the tensor product of the two things.
Yes.
Okay.
Yeah, right. I was just about to emphasize that fact. Thank you.
Okay.
The thermophile double is in the tensor product of two things, two CFTs. And remember, a CFT is a boundary of ADS. Okay. So we need two boundaries because there are two CFTs.
So is this
Right.
the right moving and the left moving, or I mean, are these dual to each other?
So it's just two CFTs, each with its own right moving and left moving factors. It's like two full CFTs.
So the duality would be between the tensor product of two CFTs and gravity in the interior. Is that the point?
Yes, gravity on a space with two bounds. Right? Because each CFT corresponds to a boundary radius.
No. My problem is that earlier you had set up the duality between quantum mechanics on the boundary and gravity in the interior, and now you suddenly taken two copies of the Hilbert space and taken the tensor product. So what is the corresponding thing in the interior?
Yeah, and sorry, I was just going to. That was the main point of this introducing this thing.
Okay.
Yeah. Thank you. Good. So I'm going to draw the state with time. And what happens is that basically you basically have a black hole. Okay, my black hole is blue. I'm sorry about that. Okay, in each side you have a black hole, but these two black holes are connected with what's known as a wormhole. This is something you might know about if you watch the movie Interstellar. Okay, and this was in fact this is a much older idea than that movie. It was discovered by ER, Einstein and Rosen, who are the E and R of EPR actually. Good, and we often.
Sorry, I have a question. So before you go further, so you are extending duality to, if I take the tensor product of the two Hilbert spaces on the boundary, that corresponds to some operation that you're doing with the two spacetimes. What is that operation?
Well, I'm not, let's see. So I'm just considering a state in this tensor product Hilbert space. And there are certain rules which I did not tell you about, which kind of tells you that there is a wormhole there between the two black holes. There are certain rules which actually tell you what the correspondence between states is. Okay.
In particular, when you take the tensor product, that corresponds to some geometric operation on the two spacetimes. Is that the point?
I won't say it's a geometric operation per se. I would not use that wording, but I feel like you probably have the right idea. It's just I would not use that wording. Yeah.
Ronak, just to ask, continue with Ramdas was asking. So you don't have one eternal black hole in one ADS3, right? Here you have like two ADS3s, like two copies of ADS.
Yeah.
It's not like so you are relating two copies of ADS, then you have two black holes in these two copies, and then you are kind of gluing them with a wormhole. And that that geometric operation in the dual theory is the thermophile double, is it? Is that the right way to?
Well, okay. Here's how I would say it. Okay, maybe a best way to say it is the following: states in the CFT are dual actually at the order we are working to geometries in the bulk. Okay, and this is equally true. States in two CFTs are dual to geometries in the bulk with two boundaries. Okay, and there are certain rules which tell you how states are related to geometry. Okay, which is not, it's not quite like taking a geometric operation.
Sorry,
all that is with one CFT, but now you're taking two CFTs and taking the tensor product. What does that correspond to at the geometry? I think that is, since that seems to be important to you, maybe you know.
Yeah.
See, because your thermophile state is in the tensor product of the two CFTs.
Yeah.
So, and that you are corresponding to some object on the geometric side. Since this is your important step, maybe you can explain this a bit better.
Well, I mean, wait, well, let me just think this through.
Maybe just I'll ask one question, Ronak, just also to clarify a little bit. So if you take single eternal black hole, so you don't like, then what is the corresponding dual state in the CFT for that?
Well, so the point is that a single eternal black hole is actually a slightly badly defined. Well, okay, the corresponding state is not a, it's something called a mixed state, which I have not defined.
Okay. And this is a pure state in the tensor product.
Yes. Yeah. Good.
So in a given CFT, you have, so given an eternal black hole in one ADS, there is some state, some mixed state, and then so given two copies of this, two eternal black holes in two different ADSs, you have like a tensor product of the two states. But when you glue it, the resulting state is this state which is thermophile double. Is that the?
No. So the entire point is that the thermophile double is a highly entangled state. As I mentioned earlier, it is in some sense just a realistic version of a bell pair. Okay, because a bell pair, all states are equally weighted, which is unrealistic because some states are very high energy. So thermophile double is a highly entangled state, right? And the point is that you cannot, because it's a highly entangled state, the thing in the bulk is not some simple operation of two ADSs or something. There are certain rules. I feel like talking through that rule would take a long time, so I will not be talking through that rule.
I'm not asking for rules. I'm asking for, see, you're making a big jump here. In particular, are you saying, just to clarify something that happened right now, are you saying that geometry in the interior corresponds to density matrices for the CFT? Because mixed state is a density matrix, right?
Mixed state is density matrix, yes.
So the correspondence is between geometry in the interior and not states of the boundary, but actually density matrices for the boundary.
Yeah. Well, yeah, technically yes, because
we are just trying to follow the outline of the talk. So that having understood that, now you're taking tensor product of the CFT on the boundary with itself. What does that correspond to in terms of geometry?
Tensor product is not an operation on the geometry.
No, but your thermophile state is a state in the tensor product. So you are somehow linking that to two de Sitter spaces, each with a black hole and a wormhole in between. So that is just saying that it follows out of some extension of the Ballasena rules.
Yes.
Okay.
Which,
Yeah.
There is a well-defined procedure to associate states in the CFT to geometries in the bulk. Okay, and that well-defined procedure gives you a wormhole. And
okay, so sorry for the long interruption. Yeah, please go ahead.
Sure.
Ronak, there is a question in the chat. I will just tell you, but before that, let me just slightly ask one more question. So suppose we do not have this wormhole. Suppose you don't have the wormhole, you only have the two eternal black holes in the two blue guys. Then still there is a complicated state in the tensor product of the two CFTs, right? Which is not the thermophile double. But it's not it's a product state, but it's not the thermophile double, of course. It's some state.
Yes.
Okay.
Yeah.
So there is a question in the chat, Ronak, that actually Govind's question.
Mhm.
What does one mean by the bulk here? Is
What
it
are-
not a is it not a Cartesian product of the individual bulk? He's asking about the two copies that you have. Yeah.
Yeah, so exactly. This is an important question. And perhaps I should have led with this. So, for example, let me take so to say in a single CFT, there's a vacuum which is dual to what's called empty ADS, which is some geometry. Okay. Then the product state is dual to two copies of empty ADS, which is a Cartesian product. Wait, is it a Cartesian product? I'm sorry, I'm blanking on the specific correct definition of Cartesian product, but it's just two copies. Okay, which was what you might expect, because there's two CFTs, so there should be two ADLs. It turns out that when you take a highly entangled state, okay, then it has to be some sum of stuff, right? Because each entangled state here, each state here is something in the bulk, maybe with some stuff in it, okay, and some sum of stuff. It turns out there are rules which tell you that the sum of stuff somehow goes into just what I drew earlier. Basically the wormhole. And yeah, I made an active choice not to talk about these rules today. So I will not be talking about them because it will take us too far afield.
Okay. Thanks. I think it answers, Ram. Thank you.
Yeah, good. And, right. So that is the point. And so, yeah. So, okay, right. Okay, yet again, the duality is between the Kohli double, which is a highly entangled state, and the wormhole.
So can I ask a question?
Mm-hmm.
Yeah. So so when you are taking this highly entangled state in the last slide, so in the last slide you are taking highly entangled state. So you are saying that the copies of the geometries that you will get is like the is like the tensor product of two bulk geometries, which is summed over, and then is that so that this wormhole picture you will get as, I mean, one of the geometries of this summed over product, or
no, it's in fact, this is one of the central points. This wormhole picture is an effective theory for the whole sum.
okay.
The whole sum is huge. It's an infinite sum in general. Okay. But what happens is that there is an effective theory for the whole sum, which is this wormhole picture, which is in fact the main point I was about to make.
Okay.
Okay. Yeah. So, right.
Thanks.
This is yeah. But let me get to that in a minute, maybe. In the order I was planning. Good. So, and a non-entangled pair of states. Sorry, that was confusing. A product state is dual to two disconnected spacetimes. Okay, and right. So what we see is that when we add entanglement, we get a connection. We get spacetime. Because at low entanglement you have disconnected spacetime. When you add entanglement, the two spacetimes connect to each other. This is known as ER equals EPR. EPR is entanglement, it's Einstein Podolsky Rosen, and ER is the wormhole. When you add entanglement, you get a wormhole. Okay. this wormhole did not exist in the product state. It exists only in the entangled state. This is a simple example of entanglement building spacetime. Okay, and as I'm drawn this, as I indicated in this picture here, the entangled state, you might think of it as a highly entangled state of some stuff, right? But there are certain rules that tell you no, there's not there's not a lot of stuff in it. There's just a wormhole. Okay. Yeah. So in that sense, you're taking a very complicated state and giving it a very simple description. And there is a word for this. It's an effective theory. So this ER equals EPR correspondence, which is really due to Maldacena Susskind. In 2013 or so, is really just this. It is a simple example of how entanglement builds spacetime. Okay. Yeah. Good.
So
that is.
Are you saying that it's not that ER equals EPR, it's that ER is a coarse graining of EPR?
Yeah, actually.
Okay.
Yeah, ER equals EPR is not quite correct. But it's a very catchy name. Yeah. The correct version is that exactly that ER is a coarse graining of EPR. By the way, there's a funny story about the ER and EPR, these two papers. There was a 5-year period, there was a 2-year period in Einstein's life where he was working on something else, and it's considered a fallow period. Both of these papers, which are foundational to us 100 years later, came out in this fallow period. Yeah. Cool. Right. So this is what I wanted to tell you about the fact that entanglement builds spacetime. Okay. Yeah. So that is the point of this part. Okay. Now, because I've run out of time, I will just summarize the result of my paper, or all the results of the paper. What we showed was that instead of taking the thermophile double, okay, we took a slightly different state, which I will write as this M(E1) E prime. This M(E) prime is just some general matrix, but the important point is that it has high rank. Okay, it's not a rank 1 matrix or something. It's a large rank matrix. And what we showed was that this state is also dual to the same black hole with what do you say? Same geometry, which is 2 black holes with a wormhole, connected by a wormhole. Right? So this is pretty interesting, because earlier we said, okay, this state is some geometry. Now I think that this different state corresponds to the same geometry. Okay. So what we have is that you have 2 states which differ on the detail, but in some sense are in a very coarse-grained way. They're very highly entangled states. They both have an approximately a set of weights approximately given by this. Okay, in here, and therefore they have the same geometry in the bulk, right? So this is similar to what I mentioned with the pan of water. You know, when you shake the pan of water lightly, there's water moving everywhere inside the pan and the entire CD space. But all of that stuff we coarse grain over it, we forget about it. And similarly what we're seeing here is that the details of the entanglement, the details of the state are forgotten about. Well, you know, there's only the information which in some sense remains is that it was a very highly entangled state. And so in that sense, this geometric description of a wormhole is a coarse graining of the entanglement in the boundary plane. Okay, and that is the main point of my talk. So that is really the punchline. Geometry is coarse graining. So the two things I explained, but as it was emphasized, I did not prove, was that A, without entanglement, you do not have that wormhole. But B, the existence of the wormhole and its details are independent of certain details of the entanglement. So the first thing is what is usually summarized as entanglement by spacetime. The second thing is what I'm saying is geometry is in fact a coarse graining of entanglement or an effective theory. And yeah, I would like to end my talk there. Thank you.
Sridhar,
Yeah. Look, if there are any questions, we can take them. Ronak, ask. You may ask something. Ramdas had some question.
yeah. Ramdas, you can just unmute and ask.
No,
Yeah,
I'm
okay.
fine.
No. And Ramdas.
Sorry. Yeah.
Hello.
So,
Yeah. Can I ask?
Yes.
Yeah. Okay. So the quantum entanglement is only one type of quantum correlation, as I understand. There are other type of non-classical correlations. So what is special about quantum entanglement here? I mean, yeah.
So that's in fact a very beautiful question, and the answer in some sense is no one is quite sure. So
Okay.
there is Adhd correlation, which is not quite entanglement, which seems to be inconsistent with the existence of classical bulk. But then there are many types of four-party entanglement, which are necessary for having this connection. So in fact, this four-party correlation is also something like Adhd, which is not quite a quantum entanglement, which is not a quite entanglement, it's some other sort of correlation. Further, it has also been shown that other three-party correlations are important, but we don't know what types are important. So
Okay.
the question of what higher party entanglement correlations are required to have a bulk is not known, and this is a very beautiful question. It's an active area of research.
Okay. Yeah.
Any other questions? Ronak, maybe I can ask a small question. So if I take a single eternal black hole, and then I look at the Einstein-Rosen bridge inside a single eternal black hole, right? That's one way to look at this wormhole solution. Like one Kohli, the space-like slice, right? In the eternal black
single two-sided eternal black hole look?
Yeah, two-sided, but in higher dimension, in ADS3.
Yeah.
So then that wormhole is, I mean, I only have one space-time, but like I don't have two copies of space-time. So that wormhole, does it have a boundary? Because that is
I'm sorry, yeah, that is the thermophic double. did not draw the Penrose diagram for it, which you would have probably been more comfortable with. I drew this very horrible cartoon, but it's exactly what I drew actually. That was just a two-sided tunnel black hole that I drew.
But we have only one CFT there. We have only one ADS.
Two-sided tunnel black hole is dual to a thermophile double slit.
But in higher dimensions,
two CFTs. It's all in all dimensions.
I see. In all dimensions, there are two CFTs. You're saying.
Because see, there are two sides, so there's two asymptotic boundaries, so there have to be two CFTs.
Okay. Okay. Thanks. So you could have just worked with one eternal black hole, right? You didn't need, I guess.
Yeah, I guess it's a semantic question of, do you consider a two-sided eternal black hole one black hole or two black holes?
Okay.
I go between the two sometimes.
There's one more message.
There's one more. I'll read it out, Ronak. So if there's a question, what is the nature of ADS-CFT duality then? Is it some kind of a adjunction relation based on what you said last? It seems like it's definitely weaker than an equivalence.
Good question. That's a very important question. And so the belief is that it is an equivalence between a complete theory of quantum gravity and the CFT. The point is that when we talk about classical spacetimes, we are really doing what's called a saddle point approximation of the complete theory. And the point is that the approximation coarse-grains over some information. And right, so that is the main thing. The strong statement, which is that the complete theory of quantum gravity, which is not classical, is dual to CFT. I feel like it has not had the most convincing proof, but people argue that it's true. But it is believed that there is an equivalence also. But you're right that at the level I was working, it was not an equivalence.
Thanks.
Do you look at a specific matrix MEE prime, or is it a generic statement?
It was very generic, in fact. Like as long as certain powers of certain traces of powers weren't small, that was scaled with 1 by G Newton in some unit, it worked.
Okay, thank you.
Yeah.
So, if I may ask a question, what exactly are the building blocks of the space-time that you're taking, the quantum mechanical states? Physically, what are they? And second part of this question, shouldn't they be indistinguishable, or are they just distinguishable? Because the way you construct entangled states usually depends on whether the constituent states are actually distinguishable or indistinguishable.
Sorry, can you repeat the first question? I blanked on it. What was the first question?
Yeah, the first question is, so this space-time you're getting by coarse-graining something. So what are the basic elements that you're using?
So good. Really, so on the boundary, we have a well-defined CFT. That is one element. And the rules for understanding CFTs are well known. And the rules for associating a state of the CFT to a state of the bulk, a geometry of the bulk, really involves doing a path integral and a saddle point approximation. That is what's called it's called some dictionaries. This is one of the most fundamental points of ADS-CFT dictionary. Using that, the equivalence between saddle point path integrals on the bulk and path integrals on the boundary, one can associate states to each other. So these are basically the two elements that one really uses, but nothing else. Yeah. And the second question was, I'm sorry, I forgot the second question.
No, the states that you're considering, are they distinguishable or indistinguishable? What do they represent?
They're distinguishable. They're energy eigenstates, right? So I'm using basically the thermophile double is made out of energy eigenstates, and definitely energy eigenstates are distinguishable because you can measure the energy, and then there are different answers to it. So they are orthonormal states in the Hilbert. Maybe that's what you were looking for. Yeah.
Okay,
Yeah.
thanks.
Okay, I think there's no other hand I see. So let's thank Ronak for a fantastic talk.
Thank you.
Thanks, Ronak. Thanks a lot.
Thank you. Yeah.
The next lecture is today at 9 p.m. right, Madhavan?
That's right. Chandrasekhar, correct.
9
9
o'clock.
o'clock. So
Yeah.
same.
Okay,
Bye,
Ronak. Thanks.
Bye,
Yeah.
Ronak.
Thank you.
Thank you.
Bye. Thanks a lot.
Bye. Yeah.
Bye.